Okay, chapter 21, radioactivity and nuclear chemistry. We are so close to the end of the course. We've only got 15 minutes, so we'll try to get through as much as we can. It's mostly reviewed to start out. Radioactivity is useful for a lot of things. One of those things is in medicine, nuclear medicine. So radioactivity is the emission of subatomic particles smaller than atoms, the particles that make up atoms often. The emission of subatomic particles or high energy electromagnetic radiation, so not having mass but having a wavelength and frequency and all that. And this happens for the nuclei of certain atoms, especially large atoms. And nuclear medicine is an area of medicine that uses radioactivity for diagnosing as well as treating disease. So one of the ways that radioactivity is helpful in nuclear medicine is that some types of radioactivity can go through the body. So you can inject somebody with a radioactive isotope, and it might find its way to a particular region of the body. For example, radioactive iodine gets taken up by thyroid cells, and then you can do some imaging to figure out where all of the thyroid cells are, if they've got thyroid cancer, for example. And you can do that also with photographic film or very, very fancy, expensive, large machines. Radioactivity has been known about for a long time. It was discovered in the late 19th century by Antoine-Henri Becquerel. He hypothesized that the greenish glow of phosphorescence, think glow-in-the-dark paint, was associated with the emission of X-rays like you get at the dentist's office. X-rays are actually invisible. He exposed some crystals to sunlight because he thought that phosphorescence and X-rays were linked. So he was trying to charge up the phosphorescence by exposing them to sunlight. And then he placed them on top of a photographic plate that had a cloth over the top of it to try to show that the X-rays were going through that cloth and into the photographic paper or photographic plate, and then causing it to develop this dark spot. As expected, there was a dark exposure spot where those crystals had been. However, he later retracted the results that he submitted to the French Academy of Science. He found a dark exposure spot even when they had not been exposed to light, and so no phosphorescence, no glow-in-the-dark effect was happening. So the crystals were emitting something by themselves. So without charging them up with phosphorescence, those crystals were emitting something that he called uranic rays, which sounds like, I don't know, something that a villain would use in a movie. More on radioactivity. Marie Curie was a Polish woman, one of the first women in France to pursue doctoral work, and she discovered two new elements in her search for other substances that emitted, still at that point, called uranic rays. One of them being polonium, named after Poland, her home country, and another being radium. And radium glows in the dark. That's why we've got a picture of a watch here. Probably not one that has uranium on it. It looks a little bit newer than that. Radium is named for its high level of radioactivity. It glows and emits heat just by itself. So old watches and old clocks, they used to actually paint. They had a special radium paint that they would use to get them to glow in the dark. So you didn't have to charge it up by exposing it to sunlight. It would just glow in the dark all the time, and people painted those on by hand. You can look up the Radium Girls if you want to learn more about that. It's a little bit grim. Curie also changed the name of uranic rays to what we now know as radioactivity. And Curie won a couple of Nobel Prizes the 1903 with Becquerel and Pierre Curie, her husband, for discovering radioactivity, and then in 1911, a Nobel Prize in Chemistry for the discovery of polonium and radium. She's one of the few people or the only person to have won 2 Nobel Prizes in different fields, something like that. A couple of people have won 2 Nobel Prizes. I think she's unique, or one of a very small number that have won them in different fields. Curie focused her work on discovering different more radioactive elements. Ernest Rutherford and others focused on characterizing radioactivity. Basically, how does it work? What does it do? What's going on? Like, what's the nuts and bolts of it? If you go and visit, I don't know where it is. I don't remember where it is. But you can go visit Curie's lab, Marie Curie's lab. You can't go into her lab, I think, because the chair that she sat at is still radioactive. There's a radioactive hotspot where she used to pull out her chair. She would grab it in the same spot and pull it out, and that area is still radioactive because they didn't know that it was really bad for you. So radioactivity on her hands went to her chair. Her notebook is also still radioactive, and I think they have that displayed in a lead glass case or something like that. So it turns out the nuclei, where the protons and neutrons are, of radioactive elements are unstable, and they spontaneously, by themselves, without any outside intervention, will decompose, and in doing so, they emit small pieces of themselves to gain stability. There are a couple of types of radioactivity listed here. These are mostly, or should mostly be reviewed, except for electron capture. That one's new to us, probably. And we'll quickly go through some of this. Okay, so reviewing nuclear symbols, since we haven't looked at them in a while, isotope symbols. We've got a couple of features of our nuclear symbols. We've got the mass number. The mass number is the amount of particles that have mass, or that have significant mass. So this is protons and neutrons. And the A stands for, I forget what the German is, but it's from German, and it's just like atomic weight, basically. And then we have the Z, which is our atomic number. Z from Zahl, I think it is, Z-A-H-L, for German number. That's just protons. So that corresponds to the number that we see on our periodic table, right? So like for helium-2, the number of protons, that's the number that they were listed in on the periodic table, like the order that they're in. So it's just the number of protons. A couple of ways to remember it. Big number over little number, A over Z. A comes before Z. We're going to put the big number over the little number. It's always going to be a bigger number on top than on the bottom. Or they'll be the same for hydrogen. And then standing in, X here is just standing in for any chemical symbol. So off of our periodic table, our 1 or 2 letter chemical symbol. Most elements have several isotopes. We refer to a particular isotope as a nuclide. So a nuclide is a single isotope. And we could represent that by listing the element name or symbol followed by the mass number. So carbon-12, for example, that's a stable isotope of carbon. It doesn't just have to be radioactive isotopes. We can list any isotope, including stable ones. So carbon-12 is the most common one. Carbon-14 would be the one that's used in carbon dating. That one's radioactive. And we can represent our main subatomic particles, protons, neutrons, and electrons, with these nuclear symbols. So for our proton, the symbol is P. It's got 1 proton, so this lower number is 1, and it's also got 1 proton, no neutrons, so the upper number is also 1. For our neutron, the symbol is N. The lower number is 0 because we have 0 protons. The upper number is 1 because that's protons plus neutrons. We've got 1 neutron and a neutron, profound. And for electrons, we've got the symbol E. We've got a -1. And the way that I think of that is because it's the opposite charge of a proton. But we have a 0 for this upper number because an electron is neither a proton nor a neutron. So we'll see those symbols in our types of radioactivity. Our first type of radioactivity is alpha decay. In alpha decay, an unstable nucleus emits an alpha particle. Convenient. So alpha decay emits an alpha particle, and it's the same as the helium nucleus. The helium nucleus, because there's no electrons that are emitted in alpha decay. So 4/2 He, that's our alpha particle. Helium's got 2 protons, 2 neutrons, so 4/2 He. And we can write out nuclear equations for things like radioactivity. A lot of our rules, a lot of our laws from earlier are the same. So mass is conserved. Meaning that we're not creating or destroying protons or neutrons. So number of protons and neutrons is the same on both sides. And in our nuclear equations, for most of them, we've got a parent nuclide that's on the left side, and then it decays to form a daughter nuclide, and then whatever the particle is for the type of decay. So this is alpha decay. So it emits an alpha particle. I don't know, I'm having so much trouble doing the alpha thing. Looks like a fish. And if you add up the top number, it'll be the same on the left side and the right side. If you add up the bottom number, it'll be the same on the left side and the right side. So let's say that we want to do a nuclear equation for the decay of polonium-216. We're going to start, I'm going to identify the information we've got, polonium-216. So polonium, the 216, is that the upper number or the lower number? It's the upper number, big number. And we can find the lower number, the Z, by looking at our periodic table. So we find polonium, and its number is 84. So the lower number here is 84. And we're told that this is undergoing alpha decay. So that means it's going to go to some daughter nuclide and 4/2 He. And then we need to figure out what the numbers of our daughter nuclide are. So we can set up a very simple set of equations. For the top, 216 equals x plus 4, because we need the top numbers to all be balanced left and right. So X just standing in for whatever our A is going to be for our daughter nuclide. And we can do a similar thing for the bottom, 84 equals Y, just so it's a different variable, plus 2. If you can do this in your head and you can get it right every single time, that's awesome, that's great. Go ahead and just do that. That's fine with me. So 216 minus 4, we're going to have 212. 84 minus 2, we're going to have 82. And then we look at our periodic table. We find number 82, the symbol Pb, meaning that we've got lead. And that would be our complete nuclear equation. Again, the top and bottom equations there are optional, but that's a way that you can solve, should be able to solve any of our nuclear equations as long as you remember the particle types. Questions about review up to alpha decay? Okay, we'll pick up probably on beta decay. I'm guessing that's the next slide. Next class, and hopefully get into some new stuff as well.